Okay, good evening to everyone. And then what we're gonna do, we're gonna continue the same discussion that we had last time. Last time we were talking about the confidence interval for the point estimate in different ways. You can remember that from homework. Number 3, I think I related to this one when I was going through this theory a little bit. Okay, so we can construct the confidence intervals using the bootstrap sampling technique. Okay, this is the way that how we do that. Last time we did elaboratively. Okay, you can do that one while I'm going through that this homework again. You can see that one very clearly. Okay, so this is that is pictorial form, and then this is how we're gonna get this upper bound and lower bound for the sample mean. This is related to this is simulated sampling distribution. First one bootstrapping, second one simulation. Kind of like a same kind of a method that we use for this one. Then third one using normally distributed sampling distribution. See, like this kind of a technique. See? So through this one, we got that. Pretty much through all these methods, we're gonna end up with the same answer. But you don't have to use all the methods, but you better learn all the methods. On my side, that I have kind of like a different kind of a mission for me to that explain everything to you guys. In that way, you can pick one of the methods and then give the answer. See? Okay. So see, T-distributed method. That's the fourth method. And we were over there. This is related to that. And while I'm going through this example, I relate this to the homework assignment on homework question number 3. See, question number 3, based on the cancer data, if you pull out that data and then the document, let me see. I'm gonna pull that up. So let me see that I have that one. Should be. Yeah, I think I have. See, this one, this data that has like a 10 variables plus this categorical one, and altogether 31 30 plus this one diagnosis plus another 10 variables. See, the radius, texture, smoothness, compactness, concavity, concave points, and then plus that it's been repeated 3 times because all these variables mean. That means each variable for each patient, it has been done several times. They measure that measurement several times. Let's say the radius has been measured several times for each patient and got the mean. And that particular patient standard error. That particular patient's mean of the 3 largest value for that one of the patient. So pretty much same fashion we did that one for so many patients. Okay. So in that way, this time 3 times 10, 30, 31 variables we have plus that ID number. So let's see that data set. Let's pull out a little bit too. See, I think here I have that one too. So sometimes, okay, it's in that Google spreadsheet. Okay, see, I'm gonna talk about that one a little bit too. Hey Magnus, you didn't miss anything, okay? I just started, okay? You didn't miss anything, I just started, okay? Don't worry about anything. I just started, I'm just telling that I just pull out that homework and try to connect this one to what I'm doing, okay?
Oh, okay.
Sure. Right. Okay, then I'm showing this one. I'm gonna show you why I got this one to Google spreadsheet for a reason, because sometimes some function on my R, it doesn't work, but it's really working on that textbook sandbox. Then how could you gonna get your data into sandbox? Okay, something I will show you today too. Anyhow, that here that the same data set. See, so that the ID and the diagnosis, and then the radius of that particular person, that the mean. We don't go to the radius, we go to the average of radius. That's That's the difference between that what we did earlier and now. And instead of that one, then we're going to go to the standard deviation of the radius. See? And then later on, we're going to go to the worst. Worst means like a largest, see, worst of the radius. Each variable has a 3 components. Worst means like you get the largest three readings and then average it. That's what the description says on this homework. Okay. See, the mean standard worst mean of the largest three of these features are captured for the image, blah, blah, like 30 features. And field 13 and radius, let's say radius in that, if the field 3 is the mean radius, field 13 should be the radius standard error. Standard error means standard deviation. And the 23rd one will be the worst radius. Anyhow, we have a 569 patients. Out of there, the 357 are healthy, 212 are deceased, malignant and benign. So I'm over here related to what I have been, here, actually this part, I'm over here, this part. So fit an empty model for the parameter mean. Parameter mean means average. For the average, I'm doing that constructing confidence interval right now. What are the parameter estimate? You know, parameter estimate, the other day we talk about that one. Parameter estimate is nothing but the y bar obs. So it's related to, see, related to this one, see. Parameter mean, if you want to see, related to homework 3 in the part 3, question number 3, part C. See? Responsive variable, there's nothing has been utilized. So then if you use the empty model, you're going to go ahead and get the mean. Mean is the grand mean. Grand mean is nothing but the y bar obs. Obs we can easily get. And we are not interested in this guy only. We need the whole bunch of values called the confidence interval, which has like a lower bound and upper bound. That's what we are trying to do using several methods. We did up to, see, using this method, we did that one. We saw that one. Then using this method, I used all this method. So see, I used this method. I'm sorry. Bootstrap method. See, bootstrapping. Let's go to the R and pull out that number 3. Before that, I'm gonna get this. I think homework. I have already got the data in. Let's go to question number 3. Okay. Question number 3. That's 3. Yeah, see, even 3, I'm on part C. Part C. Yeah, part C here. Okay. Here, see. Construction of 95 confidence interval for the population perimeter mean. See? Population perimeter mean, which is mu. See? Which is mu. Okay. I'm talking about the mu. Okay. So method 1, using bootstrap sampling distribution. Okay. Sampling distribution of y bar. Bootstrap. See, I'm going to bootstrap. Go to the resample. Go to data. My data name is that. Go to the perimeter mean. Okay. They were asking us to do that one for the perimeter mean. See. See. Find an empty model for the perimeter mean. See. This picture you can see clearly this. Yeah, here. See, perimeter mean. See. Has been explained by the empty model. Okay. So for that one, I'm constructing confidence interval. Perimeter mean estimate is the y bar obs. We know that one. You can get it easily. It's not a big deal. So I'm interested in confidence interval. So bootstrapping. See, how do you do that one? You go to the resample, get the data, go to the perimeter mean. How many patients? 569. Data sample size is this much. I got the sample. I found the mean. I'm going to do that one several times. See, boot. I get the first 6 entries of the boot. I simulate perimeter mean. I'm going to simulate the perimeter mean. See, with the aid of the sample, I already have that one. I'm going to build up the sample out of the sample. Those are fictitious sample. Those are the generated sample. this virtual samples, but I can do that one. That's the method is called the bootstrapping. That will provide the very perfect, not the perfect, like a very good answers at the end of the day, exact answers. Huh? See, I do that one, and then I'm gonna arrange that one. See, arrange from the according to that method, you're gonna arrange. Okay, arrange from those y bars will be arranged. See, I'm gonna see, I have this one, y bar 1, y bar 2, y bar, all the way up to 1000 I have. Okay, I display only the first 6. If you want, you can go to the last 6 by invoking tail. And I'm gonna arrange, go to the bootstrap that whatever the data frame, call the data variable. Once you do that one, they will be arranged from the minimum value to the maximum value. Then no longer we're gonna have this setup. See, I put the brackets. This is how you're gonna indicate. Then you know minimum value gonna come first, the maximum value gonna go to the last one. Earlier it's like a mixture. We don't know, first one not gonna be the minimum value. First one may be the some different value. Okay, by random somewhere it might be even the minimum value. Maybe this is the maximum value, but when you order from the least to the highest, it's going to be order statistics. We call the order statistics. Okay, so we're going to arrange. The code will be that arrange. See? Put it back and give the same name. See, then from that one, I'm going to go ahead and get the lower bound. I need the lower bound. Lower bound is nothing but, see, lower bound is nothing but, see, this I arranged. For this guy, we can draw the histogram. We can draw the histogram. We can draw the normal curve. We can draw the density curve. We can do all of these. Okay? We can do all of these. We can see clearly. If it is related to that homework number 1, you can see that one. You can do that one. Then I'm interested in now, I'm going to keep the 95% confidence interval. 95%, I'm sure if I construct 100 confidence interval, 95 of them going to contain the population mean within that one. So that if that's the case, I need to keep my boundaries at a certain point. That bound has to be calculated. How do you calculate? You go to the y bar. I have 1,000 of them. See, 1,000 of them. How much area to the left? How many area means number of y bars to the left of that one. How many y bars left to that one? Is I have a 0.025 to the left of as like a percentage. I'm going to multiply by that one. That will give you 25. That's the 25th order statistic. I do the same thing to get that one to the left of that one. So it is 0.95 plus 0.025, 0.975. See, I multiply by that one. So that's how you get the 975th that entry in the order statistics. See, look at, see, 1,000 has been multiplied by 2.50, 0.025, which is 25th one. That's how you got that one. See, that's the lower bound. The lower bound is 89.877 something. It might gonna change from what I had earlier. In a similar fashion, or you can do with the comma. Can you remember we had that discussion? If you go to the data frame and the variable, you don't have to put a comma. It is in the frame already. If you just simply go to the data frame, make sure that data frame you put the 25 comma and leave that that place for the columns. See, that's how you get the same answer. See, either way, either this way or that way. Then let's go to the upper bound as we display over here. See, upper bound. You go to 975th percentile. Either you can calculate like this way. If it's that 94 something. Oh, see, same thing. Then your confidence interval for mean, for the population mean, parameter mean, see, you're gonna write that one. Next page. See, you got this one, you got this way, you got this way, you got this way. Lower bound, upper bound. Come on, lower bound is 89 something. Upper bound is 90 something. Your observed value gonna be in between that one. See, your observed value would be somewhere in the middle of that one. Okay. So that's one method. The second method of in a similar fashion, I did that I generated the mean mean by assuming that my population distribution is they're normally distributed. See, 569 entries. I have to give the normal distributions mean. It's nothing but the go to the data, then parameter mean, go to standard deviation, and I do that 1,000 times. Second method, simulation. See, then arrange again, same fashion, same thing. See, you know now. See, kind of like you get the same answer. See, upper bound, lower bound. See, and you can write it like this. That's the second method. By simulation, by bootstrapping, simulation. Assuming that population parameter is known, see, assuming that the parameter mean, see, perimeter mean is normally distributed. And the third method, using normally distributed distribution, see, normally distributed distribution, that is, see, using the observed sample by like a, see, by hand, you're gonna do that one. So that, I'm telling that one is related to, you're not gonna do that one several times like this. Here also we are assuming that the normally distributed and you generate again and again and again and again and then get the 1,000 of them and then rearrange them from the least to the highest and then got the 25th and the 975th, the cutoff values. Those are the boundaries of the confidence interval. We don't do like that. We go straight to the one of them that already we have in our hand. We're going to utilize, assuming that your distribution is normally distributed. See? So straight go to the formula. You have an observed value. You go to the critical value, something we talked about the other day. And then see, margin of error is like that. See, you plug in into the formula. See, you plug in into the formula. See, lower bound is like a y bar minus critical value, S sub, see, thumb stat, go to the mean minus. How do you get the critical value? Go to the Q norm, or by convention, if it is 95%, we have a table. I gave a table. You don't have to write like a Q norm. You have a table. I gave the standard value the other day. See? If it is confidence coefficient, your confidence interval is 90%, 1.6 for your critical value. 95%, 1.95. 98, 2.32. 0.99, 2.57. You don't have to put like that. It's better off to write the codes because that's kind of that training you really need. You try to use as much R code as you can. In that way, you get a good practice. Okay. So let's do that one with the aid of that. Rather than just simply put that number, we can go ahead and then get that value so with the aid of that R code. See, Q norm, thumb stat divided by square root thumb stat n. See? So that's what I did. See, there you do the same thing with the plus sign for the upper bound. See, that's the formula say. Formula say this one, see, this one. For this one formula, y bar obs plus CC plus standard deviation observed value divided by square root 10 with the aid of only one sample. Earlier we did that one is 1,000 sample. Bootstrapping 1,000 sample. Normally that simulation 1,000 sample. That's the one technique. Second technique. Third technique. So many techniques. See? So that one, let's see how to get that one. See? I calculate the margin of error maximum part. That means I'm calculating this whole thing together, okay? Together. This whole thing called the margin of error. I'm going to show you. See? That part. This whole thing I'm going to calculate. CC. Okay? This whole thing. And then put the plus and minus from the obs value. That will give you the answer. Bounds. So I'm going to calculate. I go to the Q norm, area to the left, model stat. See? I got the statistics. Okay? Those are the statistics. I'm going to read from that statistics rather than put the values. We don't put the value because we are coding. In a coding, we never put the value. We're going to let the machine to do the work for us. That's the beauty of that programming. That's why we are using programming. See, I'm going to give the command for them to say, hey, go to this place and read it. See, go to the det and now perimeter mean. Go to the det and perimeter mean, or you can go to the model stat, see, and read S from that one. Or you go to the data and perimeter mean and get the standard deviation. Another way to get it done. Same thing, see, margin of error can be calculated and divided by the square root of, go and read the number of entries, see, to calculate, or you're going to calculate this way. It's the same thing. See? It's the same thing. See? See? And then you're going to found that upper bound. Upper bound is nothing but mean plus margin of error. So O mean you can write this way too. See, upper bound you can write that way. Lower bound the same thing. Minus the minus, like so many ways. I utilize this one simply. Utilize this formula. And the fourth method, instead of C distribution, the normal distribution, we're going to use the T distribution. We had that broader discussion the other day. See, TC. TC doesn't have a table for us to like get the value. In that way, definitely you have to write the code. See, QT, quantile. Q stand for the quantile, T for the that one. Area to the left is not enough. You have to give the degrees of freedom is nothing but n minus 1. In this case, 157 minus 1 and 156. You don't have to get that like that. You have to recall n and say, hey, subtract 1. See, I'm using the T distribution. Same thing. I go to the favorite step. I had the favorite step already. See, that one. Margin of error. See, QT. 0.975 only. I utilize 975 is more than enough to get the both of them, okay? Because that one enough, because the positive margin of error can be utilized to subtract. You might be thinking why I'm not using 0.025. No, you don't need that one. 0.025 give you negative value. So get the only this guy only. Sorry. Get this one only. It's enough. Okay? It's enough. You can add that one to that one. Okay? Okay. So let's keep going. Okay. Okay, then so 0.975 margin of error. I got with the T distribution, see, margin of error, that QT, see, one time. See, see. Upper bound, mean plus margin of error, mean plus margin of error, see. Yeah, see. Mean plus margin of error. Now again, okay, I gave the degrees of freedom. Look at how I'm going to say, go to the model stat and get the n and subtract 1. You write the code. It's very beautiful in that way. You don't have to say that 569 minus 1 or 568. No, don't put like that. We never do in coding. Coding is, you just ask him to do the work for us. Okay, machine going to do the work for us. Okay. So then when you're going to get used to that writing and then you improve your that skills, very important. It's going to go along with the theoretical aspect little bit. We don't do in heavy anything. Okay, you don't have to worry about anything. That's why I'm helping you out for everything. I want you to lay down a good foundation at this stage. In that way that you can get these things done when you go to a job at the end of the day. Okay, when you do your thesis at the end of the day, you can do a good job. See, because that now I'm that advising for one of the thesis nowadays, but sometimes they get stuck with that. They don't know how to even write that regression, that the coding. They got stuck. I was shocked, flabbergasted and stunned, and I was thinking, what's going on? Because one day that after that 1 year, you're gonna be exposed to the thesis. When the thesis come, this everything will come to one place. Then you can recall and say, hey, oh, Dr. Gunasekara did this in a different ways. Let's try to make this my thesis robust. Then the audience gonna read it. They like it. Okay. We don't do anything in deep. Just roughly, we're gonna write the code. The code will do that one. You have a formula along with that one. You don't have to worry about anything. You have a formula here. See, you have a formula here. Okay, I wrote here. So with the data of this, then now quantile, you're gonna get for the T distribution. In addition to give the area to the left, you are supposed to provide the degrees of freedom, which is n minus 1. See, that's kind of like a similar answers with margin of error plus mean of that observed value is that one. See, upper bound. See, 93 again. See, lower bound again 89 something. See, same thing. Now we come to the fifth method. The fifth method. See, this is the fourth method. Okay, the fifth one. Okay, this is the fourth one. I'm gonna write the fifth one and then continue this discussion. See, fifth one. Fifth one. See. Sorry. You see, calculating. Excuse me. Computing confidence intervals. CI. Straight from. See. From R function. Function for null or empty model. See? So we're gonna go ahead. See, you can say empty model. Empty model we have already set up, and empty model is nothing. I'm relating this one to the example I have in the book. Okay, then later on I'm gonna do that one related to that one in the homework. See, null, comma, data. This is my example for this is my node, fingers, and then you can use this function, confident, okay? confident, default, and then put the empty model inside, whatever the name you have given. See, see, this is the fun. This one shot you can get that. This is a parenthesis, not the bracket. Okay, it's not a bracket. You cannot. I think there's a. See, this one. You know that there's a bracket. Okay, confident default. Okay, so if you need upper bound, that will be the same upper bound from that one. See, if you want to extract upper bound from that one, go to the confident default of empty model. And you extract the second entry. And if you need the lower bound, confident default, so entry, see, empty model, and go to the first entry. This one is same as what? Same as method 3. When we are using normal distribution. Same as method 3. Method 3 means what? See? Assuming that normally distributed. This, see? Sorry. See? And this one, see? Like this, see? See? Like this method. See? CZ, like that. Okay? So let's use that one for the homework number 3 over there at part C. See, I call that an empty model. That's it. See, empty model. Get the empty model. Use the conf for the empty model, and if you want, you can give the level as well. I'm gonna say 0.95, 95% confidence level. See, they both will be displayed. Same thing. See, look at the areas to the left of this one. Lower bound is 2.5. Area to the right, left of upper bound is 97.5. See, if you want to extract from that one, from the CI, you can take it out. If you call that one CI, you can call that one CI. See, that's the same thing. See, this side, see. If you save this one to, if you have saved this one to CI, see, you have saved this one to CI, you can simply go and the lower bound is, oh, lower bound is, lower bound, you can go to CI 2 will give you lower bound. No, I'm sorry, upper bound. Lower bound is CI 1. CI1. Either way, either this one straight go to that one and recall all these. Same thing. See? That's number 4. Then let's go to the number 6, method 6. Okay, method 6. Number 6, method 6. Let's call the computing. You see, computing or calculating confidence interval straight from R function for empty model again. But this time we are not using, see, I have the empty model already. I'm going to write this one for my convenience one more time. LM thumb, in my case, thumb. See, in that case, okay, in this case, you don't have a thumb, we would be using the perimeter mean. Okay, that's the difference between my note and that one. And null and data would be fingers. Okay, and this time you are using confint. See, confint, not the default. If you want, you can save this one to confidence interval. See? Again, if you use the upper bound will be given by confint of the empty model of the second entry, and the lower bound confint confidence interval empty model 1 or upper bound is given by go to CI 2 and lower bound is given by CI1. This is same as what? Same as method 4. Method 4. That means when you are using what? When you are using T distribution. Okay? T distribution, same as T. On time, TC, critical T. TC. TC means critical T. Critical value based on T distribution. Critical value based on T distribution. See? See? So this one, let's try that one too. See? Then I'm gonna go delete this one already. See? If you want your empty model, you can leave the level. See? Confint. Out of this one, extract second entry, extract first entry. See? That's another way to get this. So then we have a 7th method. Method 7 based on what? Based on the rule. Okay, set rules. I'm talking about mean, okay? Method 7 using the empirical or golden, or sometimes we're going to call this one thumb, or 68, 95. Oh no, I would say I'm going to get rid of this one. In the empirical golden, or 68, 95, 99.7 rule, or the rule of thumb. Okay. What it says, see, this can be be applied only for bell shape, only for the bell-shaped distribution. Bell-shaped symmetric distributions. That is for normal distributions. Okay, for normal distributions. They say what? They say very interesting thing. They say that according to that rule, if your data are normally distributed after you draw the histogram, and then if you put the like a smooth curve scheme in that one, see, if data are normally distributed, distributed, normally distributed, they say that within one standard deviation, see, you have y bars here. Within one standard deviation, there are 68% data for sure. We have done that one previously in the other class too, and then see, that means within this, see, y bar plus 1 time s obs, see, that's the upper bound. It's the lower bound, y bar minus 1 time s obs. Within that one, y bar obs, see, you have a 68%. See? Data gonna fall within one standard deviation. See, one. See? If it is two standard deviation, within two standard deviation, 95% data gonna fall. See, 95%, 0.95. That means you have a center over here, y bar ops here. If you need the bounds, y bar ops plus 2 times s subs. Hmm? See? Y bar ops divided by, see, s subs. See? I'm gonna write this one to make it, rather than write this one ops, I think to make it clear. S subs divided by square root 10, okay? Because these are based on, see, square root 10, because these are y bars, okay? Not y, okay? Square root 10. S subs divided by square root 10. This one, y bar ops minus 2 times s subs divided by square root 10, okay? I'm gonna write here. Y bar ops minus, see, 2 times s subs divided by square root 10, see? Dividing. Go through, no? I wrote, but it's disconnected. So it's bingo. Oops. Okay. Let me connect this one. No. Give me 1 second. Something happened to the page. I cannot turn off to. Okay. Now let's charge this a little bit and then write out. No. Okay, let's connect this. Yeah, this one. Y bar. Oops. Minus 2 times S ops divided by square root 10. See? See? So when you need, see, look at this one. You don't need the CC. See? In 95%, it's 2, according to this rule. You don't have to put that critical value, ZC. That's something that you saw in this one. Can you remember that in this one? This method, fourth method, third method. Okay, we're going to put, see, CC. CC has been same thing. See? Y bar ops minus CC. We got the, according to the that 95%, according to that one, according to, if you go to the exact value, according to this table, that's the table. I missed the table. Yeah, here, see, 95% means 1.95. So almost 2. But when it comes to that empirical rule, you can, they say you don't have to worry about 1.95 of if the Q norm or T norm, sorry, TC or Q norm, Q norm or QT, like the way we are doing in number 3. See, you don't have to put this one, which is means this one, or in number fourth method, like this, or like QT in R code. They say don't put like that. You don't need to. That approximately they say put 2. If it is 68% confidence interval, you put 1. That's what they say. This is not valid for all of the percentages. This is valid for only 3 percentages only. That's the disadvantage. And the third one is what? Third one is 99.9, 99.7. See, almost everything within 3 standard deviation. So other than that, let's say 80% confidence interval if you want to find, you cannot use this method. See, 99.7%, which is 0.997. For that one, okay. See, you have a y bar ops in the center. They say this one y bar ops plus S ops 3 times over square root 10. And a similar fashion, this one, as that for this bound, this is upper bound in another way, upper bound, see, 2b. So the lower bound is, you can straight go to the lower bound and say y bar ops minus 3 times S ops square root 10. See, 3 times. If it is 99.7 confidence interval. See, this one upper bound, see, upper bound like that, lower bound like that, lower bound like that, upper bound like that. See, that's the same thing. So since we are dealing with the 95%, I put the 2. See, I put, see, method 7 using 6895 rule. See, I put 2 margin of error part 2. 2 times standard error divided by this one. See, we had that one. Model level, see, 2 times. You don't need the Q norm or Q norm or QT. See, just put 2. See, see, with that one. See, see, 89%. Then I suggest another method that using the bootstrap sampling distribution and confine together. See, look at you bootstrap. When you bootstrap, can you remember? See, look at you. See, you run this one. Look at, I'm gonna go back to the other one, other bootstrap again on the number 1 bootstrap. Okay, number 1 bootstrapping method in Q3 bootstrapping here. See, I go to the resample. From this one, get the resample, and then I get the mean. Look at how I'm doing here. Get the mean and arrange. See, arrange without any QC, sorry, critical Z or TC, nothing. See, this one. Look at here, bootstrapping. See, I bootstrap and then I fit in into the model. And you see, fitting into the model, do this one, and then I'm gonna say I need this one, the confidence interval for that one. See? Oops. See, okay, okay. It shows that, see, look at, see, 93, lower bound 90s, 90s 89, upper bound for the intercept. See, intercept. See? Intercept. Intercept means like only that Y bar only. See, intercept means this one, okay? Y bar only. See, see, 95%, 95%. See, estimate is 91. This sigma means that standard deviation, the confidence interval. If you need the standard deviation confidence interval, also that extract if you want to, if you go in that route. But we don't do that one in this class. It's too heavy. Okay, we don't need. But what I'm trying to say, you can try this one in several ways. Okay, you cannot even find this all the methods in one place in anywhere in any or go to any textbook or anything like that. I spend a lot of time to put all the pieces together. So get the best use of it when you see. But when you do the homework, you don't have to use all the method. Just pick one of them and then easiest method, confint or something, and then give me the answer. But you learn, okay? I cannot just simply teach this one and then do like that. I want you to broaden your knowledge in every aspect, okay? So this one has been done in several ways. I'm talking about this part C of confidence interval for mean right in this part. Sorry. We did that one in 8 methods. Okay. Anyhow, we do the confidence interval for all of these in the similar fashion. Okay. For pretty much everything. Okay. So since that part is done on top of that one, I mean, like if you go to that one, what are the parameter estimate is the Y bar ops. Okay. This one. Pre you can easily get if you run what? ANOVA and supernova. Those things will give you that one, especially supernova. For that one, okay. Let's go back to that. Systematically, we can answer now, okay? Since I'm gonna stop over here for Y bar, then since that I built up that discussion to Y bar, let's go to this one. Let's answer from here. See, descriptive statistic, quantitative variables are perimeter mean and texture mean. Create a histogram for each variable. Obtain 5-number summaries for each variable. Okay, let's try to answer question number 1, part A, 1 and 2. Roman numerals 1 and 2. Let's go ahead. Okay. I hope this we have all. They say put that F size for the Cohen's D later on. Supernova, but I don't know that I have an issue on my that R that even the supernova installed, the table will be displayed, but the B0, B1, this is what I'm trying to say. This is supernova package should produce, the supernova package should produce all these. B0. When you put the B0, it should extract the intercept. It should extract the slope. It should extract the F value. It should extract the pre. It should extract the SSE. It should extract the SS regression. No? These two are aliases. Same thing. Okay. Excuse me. But for certain reason, it doesn't work. But fortunately, if you go to that, our textbook, see, on the textbook, it works. Textbook works. But in the question, this data, we have to get into that the sandbox. That part I will show you too. Okay. This data, see, this when I put I extracted that data, same data, to a sandbox. It's on, see, chapter 2 on page under 2.6, okay? There, how to get the data. Okay, long time ago. Okay, that means, see, that's the data, same data I extracted. No, not this part, I'm working here, okay? So, see, when I put, sorry, when I put V1 works. But on my R, for a certain reason, V1, because they have already installed all the pretty much everything, all the packages already within this interactive textbook. That's the beauty of it. But on my R, it doesn't work. But that's okay. When we have any issue, we can jump into that one and get things done. Okay. But this should give you all these functions that I showed you over here on this one. These are the function D naught. D naught means like an intercept, slope, F value, proportional reduction in error, sum of squared error, sum of squared regression. All these can be extracted. Okay, but for my case, it doesn't work. Let's jump into this one. And let's go ahead and get the part A1. See, they were looking for, I'm just writing the favorite stat first. Okay, look at parameter. See, they got that one. Oh, if I need from that one mean and standard deviation only, see, I'm going to select mean and standard deviation from my favorite stat like this way. See, only 2 will be displayed if you want to do like that. Okay, use this command. I ran that one, parameter stat. I'm going to run the parameter stat, the mean, its favorite statistics. Then I want to draw that histogram. Look at that. I'm using the D histogram, okay, density histogram, perimeter mean, data dat. I put a color and it's connected to link to that density. I'm drawing that density curve as well. Density curve means this one. Oh, sorry, let me show you. See, this is density curve. This one. Smooth curve scheming that one. Not that formal shape. It doesn't have a formal shape, but I'm taking like a smooth curve scheme in the top of the histogram in such a way that as much that the maximum of the area gonna come under the curve. Some are not being covered, that's okay. It's approximations. We do approximation on that. In addition to that one, I do another curve. See, that's called the approximate normal curve, 2 curves. How do you get the density curve? What's the code for the density curve? See, density, and give a color, orange. And for the normal curve, I'm going to give a GF dist, normal, color. Normal means what type of distribution you need. Color I gave. I have to list the parameter. Parameter you can recall from the statistics and say mean or like that. See? And the V, I'm going to put the like a vertical line at the x-intercept. Parameter means that means. See? So let's draw this one. All will be displayed. See? See? The green colored one. So sorry, I'm sorry. The density curve is the orange colored one. See, look at like that. The blue colored one is a smooth curve. It's not a smooth curve, approximate curve. You can work with rather than working with the histogram, throw with the histogram to the side. And rather than working with the density curve, you cannot work with that one easily because so many bumps, so many more the modes, the multi-mode data very hard to tackle. That's why we're going to go to something that very familiar and cannot handle easily, which is called the normal distribution. Something has this kind of a formal shape. We work with that one and we get the approximate value and say this look like this one, like that. But it's not the way how we do when we come to the advanced techniques we have to utilize, but it doesn't matter for at the primary stage. Think about by these three things. You have a histogram, you have a density curve, you have this normal curve, 3 things. See? So same thing that I did for that. See? Oh, you can recall this one. You go see how to recall. See, go to the perimeter stat and you can say, give me the First row, sixth entry. See, you can tell like that too. See, rather than meaning, you go to the perimeter mean stat and you don't have to put mean. You can say 1 comma 6. That's the sixth entry. 1, 2, 3, 4, 5, sixth entry. Read the sixth entry. Similar fashion, seventh entry, standard deviation. See, see? You can do it in a different way. Oops, something happened. Let me see what happened. Okay. Uh, we need to install this one. We need to, sorry. Let's see. Get the message. It can come. It's not loading. Let me see. I'm gonna try one more time. This one. But early it works, no? Oops. Did I run this one? Oh yeah. Let me see. I'm gonna run this one more time. Yeah. See? You have to run one more time. It forgets. Yeah. You can recall like that. And texture for the texture too, you have to do the texture one in a similar fashion. See? That you can recall. Or this way, if you want to narrow down to that mean and standard deviation only, and a similar setup, see? Or this way again. So on the other hand, if you rather than go to that one, if you need the summary statistics of both of them at the same time, you can do that one too. Look at what I'm going to do. I'm going to recall the summary statistics means whatever I really need. I need the mean and standard deviation only. See, look at. I use the apply, go to data, and say, see, perimeter mean and texture mean together, see, with the concatenated or combined. And margin is 2, see. They do row wise, see, function, mean and mean x, see, standard deviation, see. Okay, mean and standard deviation you can recall. If you need any more, let's say summary statistics, I'm going to do that one later. You can come and say minimum value, quartile 1, quartile 2, quartile 3. Both you can tackle at the same time. Especially, I'm not talking about one, both are quantitative variables. Okay, both are quantitative variables. One is quantitative, one is categorical. You can extract that one. That's a different thing. But both are quantitative variable. If you want, you can do like that. From that one, how could you gonna extract? See, look at this like a that matrix now. From the matrix, I'm gonna say with the aid of this one, I'm gonna say give the mean. See, I need the parameters to that perimeter mean that same this graph histogram. I need the density curve. I need the normal curve, but the normal curve need the mean. See, look at how I extract the mean. Go to the 1 by 1 comma 1. See, first row, first column. See, this one means first row, first column. Then standard deviation means second row, first column. See, I recall that one. And the V line, the same thing. See, and look at here. See, and first row, second column. See, first row, second column. That's why 1 comma 2. The other one, second row, second column to get the standard deviation of the texture mean. You can do like that, please do. And on the other hand, if you need the summary statistics for both of them at the same time, as I said earlier, see minimum quantile, see quantile. Give me the quantile of 0.25. Give me the quantile of 50. Give the quantile of 75. Give me the max. See, it's a function. X means like whatever the value they have, they're going to put it over there. Both they tackle at the same time. Okay, tackle at the same time. See, minimum 25th means first quartile. 50th means second quartile. You have to give the XN percentage. 75th means third quartile and maximum. Those are the 5 numbers summary. See, favorite stat. See, Does this work? No. See, that doesn't work. This one you cannot put like that. This doesn't work. That's why we go like that. Okay? This is the only way that you can get the final answer. See, there's the same thing they're gonna ask about that later on in question number 2. Obtain 5 number summaries for each variable. So if I go see part A, second one, see, you can get several ways. You can get the full set. You can narrow down, see whatever you want. You go to the favorite stat and say that tilde and texture and then variable and then the data, or then data and variable. Many ways. And fav stat, see, again you can narrow down whatever you want. You go to finum, you go to summary, and extract what you need. Same thing you did for the perimeter mean as well. Oh, I'm sorry. Texture mean, that one for the texture mean, this one for the perimeter mean. Same thing in different ways. Okay. It's not hard. Okay. Can have a look at it. See. Okay. Then let's go to part B, categorical variable. You are using this one. Okay. You are using this categorical variable to explain whom? Perimeter mean. Who will be the external variable? Not this guy, not the perimeter mean. The diagnosis. Okay. This is always response. Okay. To create a box plot with perimeter mean, taking this guy as the explanatory variable. That's what it says, the way that they have that written this. Create a box plot with perimeter mean. This is y. And taking this one as a explanatory variable. Okay. So, so I'm going to add something to here. I can say, sorry, to make it clear. Response variable here. Response variable would be perimeter mean, which is quantitative variable. Perimeter mean quantitative variable. Okay, this one. Variable. Perimeter mean the quantitative variable, and this one is explanatory variable. This is perimeter mean. Explanatory mean means y equals that one, y. The other one, and variable, which is x. X is not perimeter mean, diagnosis. The categorical. It's a cat variable. Okay, explanatory. That's what they say. See, we're gonna draw the box plot. Go this one. Go to data. See, you can see how these we that compared and contrasted benign and malignant patients. See, they both are called the patient. The one these are called the malignant are called the diseased patients. These are healthy patients, benign. Then you're gonna run, if you want, you can run the regression. See, perimeter mean versus this one. And then group that you can get the results. See, 78.8. This is the B node. This is the B1. This is the average perimeter mean for the people in this group, benign group. No, this is see benign to say malignant. It's gonna go to malignant. That's why I put this one. See, diagnosis, but this will be for the malignant with this gap. Supernova. I hope that is already that's the table. But if I run, as I said earlier, that if I run B1, see, look at if I run the B1 on that group model, unfortunately, it doesn't work. You say it is not there. It should be there. I'm trying to extract B1 from that. Now, see, it's not there. Argument to what is that? From the group model, we can easily extract that. But if you go here, see, okay, this one, this is something like that. That B1 I'm trying to extract from a certain regression model. See? So where is that B1? No, it seems like it's gonna run all the way up to here. Okay, I'm gonna run this one more time. It shows all of them. See, gives a value, but here it doesn't. One more time. See, Y is missing with no default. Why? Which one? Okay, that's okay. But anyhow, so here, see, here, see, this one, see, we get the perimeter mean, see. So I go to this one, see. One, one. This related to Q1 part B, okay? But I'm trying to say, see, this time they have included this one. Y would be perimeter mean, see. Cont. This one X would be diagnosis. Categorical, see. So this one benign, this one malignancy. So you have patients here, you have patients here. So they are, see, Y bar of benign, see, Y bar of malignant. So this gap is B1, see, is B1. This is B naught. B naught is how much? B naught, we got 78.08. 78.08. This gap 37.29. 37.29. See, that's what they say. How many patients in each one? That's why they say, okay, later on they say, what's the next question? We can relate to this one. Create a box plot. Frequency of the two categories. Okay, two categories. It's easy. We know how to get that one. Okay, tally, or you use the table or F table, anything. See, tally with the diagnosis. See, okay, benign how many? 357. We know that one. See, 357. See, number of patients in NB 357. Number of patients in malignant 212. See? Like that. I put that in, see, NB. Oh, sorry, this one B. Okay, not T. NB. NB means 357. NM, number of people, patients in 212, and this one. You can denote like that. So, see, tally, go to data and go to diagnosis. Same thing, table, F table, they all produce the same thing. Okay, that's part B, session number 1. Create a box plot, mean and explanatory. Obtain the frequencies. Question number 2, Roman numerals. Obtain mean and standard deviation of perimeter mean aggregated by diagnosis. See? As I said earlier, now you can do aggregate one. See? With the aggregate. See? Aggregate one perimeter by diagnosis. See? Function is mean. See? They do both groups. See? Standard deviation you can get. Both mean and standard deviation together you can get. See? Aggregate perimeter mean diagnosis data that and to create a function like that. Function. See? See? Or you can do like this way. You're going to filter out malignant ones. You're going to filter out malignant ones. Keep the benign cells. Include only benign. I need the go to the diagnosis. Say keep the benign. See, and then head. See, these are the those are the data. See, my data benign, and they give the stat for perimeter mean that belongs only to benign diagnosis. See, get the statistics for the benign people statistics. See, my data stat. Go to the mean. Go to the standard deviation. Would that be the same? I narrowed, see, 78 and 11 for the benign people. 7807, 11.8, see, same thing. I filter out. I filter out malignant and then filter and keep that benign ones. Same thing you do the other way around for the filter out the benign and they keep the malignant. Okay, you can do like that. Okay. And then for their favorite stat, you go to my data M, okay, not the my data M. You're going to consider that group only one at a time and get the favorite stats for those people. See? See? I'm sorry, that's not. Then let's say that can we get the aggregate and then get this one at the same time for the both separately. Okay, then data. No, because it's already we got that one. This another. I'm sorry, we did this one. You don't have to go back to that. See, see. So another way to do that one, if you want to do that one. So these are you have seen that if you want to that get the averages not for that way. See the so just for two of them. See here, look at it. See perimeter mean by diagnosis. Okay, remember this one. By diagnosis, we check the perimeter. But I'm trying to do over here. This is not related to this one. If you really need the perimeter and texture means that mean only, you can do that one row wise. They're gonna just to simply that they're gonna find the mean value. See, that's a different story. See, if you want both together, you can do like that. And if you want to narrow down to just to 3 to 32 variables only, see, cut off that first one and the malignant, sorry, the diagnosis and then this one, see, diagnosis and the, sorry, this one, ID, see, these two cut off and you can start from here, 3 to 32. See, like that, that's another way to get, but it's not related to this one, you don't have to worry about it. Okay, then the second one, correlation between the perimeter mean and texture mean. Now both are, now both are what? Both are quantitative, not anymore. Okay, that's a regression model. We have an empty model. Look at this one. Very nicely we see. See, see, this one descriptive. This one. See, we get the empty model. Sorry, we're gonna go to the empty model later on. I'm sorry, this is the empty model. See, we got the group model, regression model. Okay, and the third one empty model. Okay, they go that they have mixed them up. That doesn't matter. See, correlation between perimeter mean and texture mean. Look at what they were doing now. See, this one group model. This part, see, this is a group model. It's a group model. So this one, again on the color. Okay. Yeah, that's okay. So this one regression model. See? This time you have see y perimeter mean simple. This one is quantitative. This one x texture mean. So also quantitative. See? So they have data go like this. See? Oops. Okay, so we get the best thing like that. So the correlation means that how strongly, how closely these data points are spread out along this regression line, or how what is the measure of that's the measure of the strength between these two variables. See, we know that one. That discussion we have done this one so many times. See, A, you can put the co. See, or you can convert them to Z scores. See, Z scores. Don't worry about this. Okay, for time being. Z score. See, you go to Z score. See, Z score, get the data, go to the perimeter mean. Now you're going to call the Z perimeter mean. You do the same thing for texture mean, convert it into the standardized one. We had that discussion. And then you're going to fit in those Z values. See? And then go get the regression model. And the read is slope. See? Slope. That's the same thing. See? 0.3295, 0.3295. 3.295 to the power of -1 means 0.3295. Same thing. If I run B1, doesn't run. See? See? Something is missing. See? But earlier say that it's not available. Okay, I'm gonna go ahead and then, but the supernova already over there. Okay, look at here then. What I'm trying to say here related to this discussion, okay, related to this discussion, let's go ahead and see that how to, if by any chance, if it's not working, how to get the everything into sandbox and work it, okay? Okay, I'm gonna go here, okay? What do you have to do? You're gonna go ahead and open, okay? Open. Google, see? You have to have your own personal one, see? Google Sheet. See? Open Google Sheet. See? Blank sheet. See? Then you go ahead and import data from where you have saved. Okay, you're gonna, sorry. It doesn't work. Okay, fine. Import. Upload. Yeah, upload. Okay, let's go to the upload. So you go ahead and see where your data is at. Let's say that I have data. See, see, I'm gonna pull this out of this one. Go to National University 605 and Simon's homework week 3. Okay. Week 3 in Pixel 5, number, diamond, number, see, cancel data, see, import data, see, I, see, it's already in this one, see, it's already in the Google Sheet. Because that data, there's no way other way that you have to give to the that space means to the online. From the online we extract. That's the trick over here. There's no other way that you can get that one straight into like R. You can recall that one. See? But there's no way that we can extract that one. You can they want us to put into the Google sheet. I'm sorry. See? See? The easiest way to get your data into data camp is through the Google sheet. See? Here's a step by step with an example. Okay, now we did that part. Okay, we got that one into our Google sheet. It's in the Google sheet now. So let's say this one. Now what I'm gonna do, I go to the file and go to share and publish. Sorry, publish to web. See, publish to web. Go to there and go and pick comma separated value and publish. Are you sure? Yes. See, they're gonna give you this link. Copy that one, that URL, copy it. Then come back to that sandbox. Come back to the sandbox. And then say whatever the name read.csv. Within that one, you paste it. See, see, within this double inverted commas or quotation marks, you just copy and paste read that, and I call the data for that one. But since already that these ones already have, so because of that, that's the way how you're gonna get the data into this one. I'm gonna do what I'm gonna do. I get rid of this one first. Okay. Well, data in already. Data in. Okay. And data in that, let's go to that whatever we have in R. In this part, now I call the same names, copy. And then I'm gonna come to my sandbox. This one, this all run together and B1. Okay, let's see. See, 0.3291. See, B1 is 0.3291. So extract. It works over here. But early it was telling on that my R1, I had to have a look at it again. That we say why is missing with the no default. Not that one, not the error that I had earlier. I say that this B1 is not available. I had to have a look at it. So I'm talking about this one. This is the way, another way to get the correlation coefficient. But I had another way to extract that one. What I did was that I wrote the slope. Slope is nothing but, see, I created a function. I created a function. See? If it doesn't work, I created a function. The slope is nothing but, see, you can create your own functions too if that's the case. Okay? The slope, I'm talking about that this equation is y hat plus b naught plus b1x. You know that. So the b1 is how they have evaluated that now. That's nothing but, see, summation, see, sum x minus x bar times y minus y bar. Take that one and then sum them up separately. And divided by summation of x minus x bar squared. Right? And b naught is nothing but y bar minus b1 times x bar. Those are the formulas. Okay? Excuse me. It wasn't working over there, then I use this one. See, sum of x minus x bar See, go to the function. See, you create your own function. I call that one slope 1. It's slope 1 function. See, you give the parameter. You know, in a function, if you create a function, this is called the function. These are called the parameter. This is called the body of the this function. See, you start from here, you get it from here. When you want to recall something, you go and tell to this guy, hey, calculate that one for me. But they say they cannot calculate, they need X and Y. You have to provide X and Y. See, this is how we're gonna do later. But see, look at it. If you want, you can write this on with the one line. See, you don't have to say mean X, mean of X is X means that this whatever the X, okay, whatever the X value, that means will be called mean X. Whatever the Y value, mean Y. Then the sum of X minus mean X times Y minus mean Y, their summation you're gonna find. That's why I see this product go together in that formula, and then you're gonna sum them up. That for the numerator. It's actually not the num. Should be numerator num. See, numerator part. I'm talking about the numerator part. This part. See, numerator part they calculate. Then denominator part. The denominator part we're gonna calculate like this. See, X minus this one, that whole thing square, and then sum them up. And this divided by and return m. M means nothing but the slope. But if you need that one, because we used to call that one m, doesn't matter. See, we're gonna run this one slope. Okay, let's run this. Okay, it's in good shape. Okay, now I go to my function and say slope 1. I'm gonna give you C texture mean. See, Z texture mean. That's my X. Z perimeter mean. Okay, I gave that one and call the gradient. See, they give the same value. Or there's another formula that you can use. Covariance divided by variance. See, look at it. Covariance divided by variance of X. It's nothing but this one same as covariance between X and Y divided by variance of X. See, look at it. See? You can build up that one. I call that one gradient. Gradient means it's another name for the slope, okay? Any name you can give, doesn't matter. See? Covariance versus this one. See, I call that one slope 2. And I'm gonna give the parameter. What are the parameters again? Z return, C texture mean and C parameter mean, and then gradient 2. See, look at the same answer. And if you need the intercept is nothing but y bar minus b1. b1 we call the m here, see, in our function m, b1 times x bar. See? Look at that function, even I'm going to call that an intercept. You go ahead and say, hey, give me the intercept. They say, in order to give the intercept, give me the parameters. These 3 parameters. You need to give x, you need to give y, you need to give the 1. M means whatever the slope you already calculate, gradient 1 or gradient 2. See, that will give you the, see, that's the intercept. See, or you can go to the intercept with the aid of the second one, gradient 2. You pretty much get the same thing. See, almost 0. Almost 0. See, same thing. See, then if you want to, that's why I say that when we're going to try to do this one with the aid of B1 doesn't work, I'm going to use that instead of B1 resampling. See, B1, see, I'm going to go to this one. See, perimeter mean, texture mean, and the slope. For the slope, what you are supposed to do for the, see, okay, what you are supposed to provide for them. You're supposed to provide them this function, slope function. If you go to slope here, slope 1 function, you try to give the x coordinate, x and y coordinate, y values. See? Go to the resample. If you're gonna resample data through this one, from that one you go to the perimeter mean. That my X. You resample. From that one you do the texture, this one. You resample and then get the perimeter mean. See, get this one, and then the calculate slope for each one, each entry. See, with the aid of all the 569 entries. See, and then do that 1,000 times. See, they display. See, generate. You need that one later on because but if that doesn't work, sorry, doesn't work, you can go to that kind of a function built up, and through the built-in up that you can get this done. And if you come back to sorry, this one, even the pre one is not working on my one. See, could not find the function pre. So this one doesn't work. Regression model, go to pre and get the square root. That will give you the correlation as well. Okay, I'm talking about the correlation. So here in the middle of built-in of the correlation, in order to build up the correlation, you get the second method. See, it's a second method all the way up to here. Or correlation, you can go to the pre and then regression. Let's try to get the pre and sorry, I'm gonna run this one on that one and see whether we can get it on that sandbox. Regression model. Not this one, okay? Not this one. I'm talking about we have to run this guy. We have to run the regular regression. Regression model. Where's the regression model? Regression, not this one, not based on this one. Not based on Z. Regression model. Do we have somewhere regression model? Perimeter mean, texture, samples, cut, summary, box plot. We call the group model. Okay, that's a group model. This one expands, correlation. Where is the intercept? This one, where's the regression model? Did we run the regression model anywhere? Okay, I'm gonna build up this one here. Okay, anyhow, I'm gonna build up here. Regression model, nothing but LM, perimeter, mean, tilde, texture, mean, data, plus that. That's the regression model. Okay, for that one, no, that they say that one. Okay, I'm gonna get these two together. Go back to my sandbox. It's not related to this one. It's a square root of the. Let's see whether okay, regression model pre, and they take the square root on that one will give you the R2. See, it gives that one too. See, it works on this one. But on my R, it doesn't. Sometime on your one, it might gonna work. Go to the see ANOVA table. See ANOVA table of regression model. You can say ANOVA table of regression model. See, look like this one. From that one, you can get the texture mean sum of squared. And from that one, you can get the residual sum of squared. Then A divided by, A means this value divided by the total you don't see here. And then get the pre. That's another way to get that one. See, pre. And find the square root on that one. That's the same thing, correlation coefficient. And then they're going to ask what's the definition of that one. We're going to give the definition. They say that, okay, that part. See? Obtain the mean and standard deviation. One obtain frequency, this one obtain standard deviation perimeter aggregated by this one. Correlation, obtain the correlation, interpret the correlation. Reference assignment 1 for example. See, or you can tell like that with an increment of 0.33 standard deviations. 0.33 standard deviations. See, I'm going to round this to 2 decimal places. Standard deviation of the perimeter mean should be added on for every one standard deviation. I'm going to talk about this one in terms of standard deviation. Standard deviation, why? With the aid of this one. It's another way to explain this. With the aid of this one, standard deviation. Standardized means standard deviation, same thing. Instead of talking about the perimeter mean, see what I'm trying to say, instead of talking about this slope like this way, I prefer to talk this one like this way. Z texture mean. Z texture mean. Here what? Z, the x value is nothing but x equals x variable is this one. Y variable would be Z perimeter mean. Standardized one. How do you standardize? You know how to standardize? You get the texture mean, you subtract what? The mean of, see, the mean of the, go to the det and texture mean. It's mean divided by standard deviation of, go to the data and texture mean, see. Texture, sorry, mean. See, this one, the numerator, see, that's texture. Texture mean. See, here, see, this one, how do you do this one? Perimeter mean, subtract mean of, go to data, perimeter mean, divided by standard deviation of, that's how they get that one. But in our code, it's called Z, okay? SD. Okay, go to that. Perimeter mean. Perimeter mean, see? Mean, okay? You know what I mean. Okay, sometimes the span has some issues. Span has some issue, okay? So this one, this part I'm talking about, see? C score, see? See, C score. The same thing equals to in R, T score, see, go to that texture mean easily for everybody, see, in R, this is in R, C score, see, go to that perimeter mean. When you draw this one, see, for something like that, see, this one, perimeter, that dollar sign, okay, perimeter mean. See, when you do like that, see, this slope is R, see, this slope equals to correlation coefficient, which is simple R. To make it more specific, I'm going to say sample correlation coefficient. Which is simple R. R, the slope. See, that's why I say that if you're going to talk about that slope, they say the standard deviation. How many standard deviation and how many standards? See, given in standard deviation, given height means a rise, no? Can you remember rise given in standard deviations? This one what? Length, the length and means run given in standard deviation as well. So instead of talking like a just regular one, we come to this framework and then talk about correlation coefficient as like a slope. Increment in one standard deviation in one y. See how if you're going to increase that standard deviation of this one, how much standard deviation going to go up on this one is called the correlation coefficient. That's what they see. Another way to explain that one. That's why we wrote like that for you to learn in different ways. An increment of 0.33 standard deviation of perimeter mean should be added on for every one standard deviation of the texture mean. Like that, okay? Or point estimate R of the population correlation coefficient rho. Now I'm going to add a new thing to here. See, relate to this one. This counterpart is called the population. Okay? Correlation coefficient, which is denoted by rho. Greek letter rho. See, rho like this, okay? Rho like that. So that means what? The best estimate for the whole population correlation based on the whole everybody, rather than talking about this only 569 patients. I'm going to talk about all the patients that going to come to that particular hospital, that particular that region, district, state, country, whole world. It depends on how you have that defined that your population. Okay, doesn't matter. It seems that let's say they go to a hospital, it's a huge hospital, and then you pick like a certain number of patients. That patients will be taken as a like a based on that one. You're gonna make the inferences, but you have to that talk about the whole population on average. That in that scenario, you have to decide which part we're going to take into account as the population. Let's say that you want to do some kind of experiment in a certain area, certain city, town, any area that you have like a one hospital. Then if you want to expand that part of that whole USA, it's very tedious task because that with the aid of that small sample, if you're trying to generalize for the whole population across the USA, it's not fair. Then you have to do so many that testing because they were nested within like that particular city has been nested within like a state, district, and then regions like that. So you have to go and then do that one in every that geographical that regions. But it's very tedious. Those are called the nested design. But at the primary stage, we don't talk about that one because we cannot mix up everything. We primarily we say that okay, you do experiment, you take the data. And that's not the case. This getting very nasty and then heavier at the end of the day if you really want to do the best job. The because that's why most of the cases that when you do the survey, you have to be careful that you generalize that one, make the inference that for that particular case, that only for the hospital, that's okay. But that one you cannot expand to like a district and say, hey, for the whole district. Like then, if that's the case, in addition to nested design within the same region, you go ahead and pick so many hospitals. That called the meta-analysis. Meta-analysis and then put the pieces together and then see that what would be the best result. Like that in a, if you really want to know which airline would provide the best customer service, you cannot simply walk into that one. You have to take that airlines and then see then put together at the end of the day, combine, called the meta-analysis. Like some in the in the laboratory that this testing, even that we have to do like, but it's very tedious and then time consuming, costs a lot. Because of that, when it comes to the real picture, sometimes that even though we use that heavy statistical procedures or data analysis, anything, we don't get the best results at the end of the day for that particular reason, for the tediousness and the cost and then the labor and everything and then time framework. Okay. Anyhow, That primary stage that we have to learn the basic and then expand it. So this one coefficient, we can call the correlation coefficient rho. So I can say the best estimate for the population correlation coefficient, okay? Simply I say correlation rho is the sample correlation, which is R, rho. I'm sorry, this one doesn't show clearly. Not the rho. Correlation, comma R, comma R. Okay, I'm going to write it. So that means rho hat is simple R. Simple R. Simple R. That's the basis to that's the say that. See, point estimate of the, that's a point estimate, okay, not the interval estimate. Rho between parameter mean and texture mean rho hat, which is R, is 0.33. Sample correlation coefficient between parameter mean and texture mean, which is sample correlation and the sample texture correlation between parameter mean and texture mean. In part C, they're going to ask about the confidence interval. They say, I'm not interested in the point estimate. Give me the 95% confidence interval for even the correlation. Even for the correlation, they are not interested in only that one point value. They need the whole bunch of values. Whole bunch of values. See, whole bunch of values. For that part, okay. Okay, that can be done by the code test. Perimeter mean, texture mean, okay. Confidence interval level has been given, conf dot level 0.95. Okay. Look at here. This is the point estimate. We saw that one. These are the interval estimate. It's going to go from 0.25 to 0.40, but my value is 0.32. It's going to be between those two. See, or code test, you can say method, you can say the method Pearson method has been provided for the parametric setting. Spearman has been set up that introduced for the non-parametric setting. We don't talk about the non-parametric, means we don't use the distribution at all. That's a different kind of a framework. That's a different kind of a discussion. But here we are based on the classical framework. I'm working on the classical framework, the regular framework. Okay, we call the classical. So in that setting, we use the distribution, we use the histogram, we use the parameters. Those are based on the Pearson. See, you can give like this if you want. I'm sorry. See. So on the other hand, see, then you can say confidence interval estimate for the population correlation coefficient. It's nothing but confidence interval. See, this is what I have written over here. CI, see, this is the point estimate. See, point estimate of the population correlation. That's that. Now I need the interval estimate. Interval estimate of the population correlation. Okay, I'm gonna stop over here because I had to jump into the other class. Okay, correlation. We're gonna say confidence. See, correlation, confidence interval for rho. Okay, we got point. I'm sorry, estimate interval estimate of the population correlation. Population correlation, see, for rho is nothing but that one will give 0.25 and then see 0.25 and 0.40 because I'm going to keep to the two decimal. This one is 0.25 to 0.40. Sorry, this one. 40. Then our point estimate is nothing but 0.33. Can you remember? 0.33. See? So in this line, see, in this row line, see, you have, see, the R you have here 0.25, you have a somewhere here 0.40, you have a 0.33. This is the OBS value. R OBS, if you want, you can say R OBS. Can you generate R? Yes. It's another way I'm going to make it more specific based on the observed value. See, R OBS more specifically. See, you want R, see, can say R or R OBS. See, the same thing. See, see, for row, you can get the point estimate or you can get the interval estimate, means any value in between this one. See, any value. That's the interval. It's the C. CI for row. It's the row hat, see, which is R, which is this one, R OBS. Like that. So this one and this one. But this one we can calculate by hand too, because we have a mechanism to calculate by hand. That's okay. See, so this one, see, that one, see, like that. See? We can come to that one later on. Okay, I'm gonna skip for time being. And part D, same thing. Okay, can see. Part D, same. We're gonna use the 0.75. See, use the same thing. Are you confident that the true population correlation could be 0? We can talk about that one tomorrow. See, the same thing you can do for with the see co1. See, now to change. See, oops, sorry. Either this way. See, 4.75. See, 75%. See, interval. So here that this means that within this one, see, within this one, see, within this one you have what? 95% correlation being included over there. See, in the second one that you have the 75% like that. Okay, the same question. Okay, so we can then we can calculate. I can show you that then how to answer the other one based on the p-value. Then we have to jump into p-value. See, we keep going and then that finish tomorrow. Okay, so do you guys have that any questions? If not, I'm gonna let you go because I have to jump to the other class. That you guys have a good night and stay safe and be well. And then see you tomorrow. Okay, take care. Have a good night. Thank you very much. Okay. Thank you. Thank you very much. Thanks. Yeah, thank you very much. Thank you. Take care. Okay. See you tomorrow. Good night.